So let's refresh our memory concerning the limit comparison test. I'll just write down the statement again. It says if, first of all, an and bn must be positive for all n. This is the restriction. You can only use this is true for the ordinary comparison test also. You can only use the comparison test if your terms in your sequence or series are always positive. But anyway, if they're positive for all n, and if this limit n goes to infinity, an over bn exists, and, well, I call this C usually. It has to exist and be greater than 0. Then, the series of an and the series of bn have the same convergence property. Either they both converge or they both diverge. This is the limit comparison test. All right. This is, once you know what's up, this is, in my opinion, a bit easier than the other comparison tests because you don't have to actually think about any inequalities, which are kind of a pain to make sure you get them straight. This one, all you have to do is set up this limit and then show that the limit exists and is positive. That's all there is to it. So I had a couple examples, and then I got some for all y'alls to try. Let's try. I did a simple one last time. Let's try a less simple one. How about this here? All right. Your job is to say whether this converges or not. Does it converge? All right. Now, like I said, you don't actually have to work out any inequalities if you're going to use the limit comparison test, but you still do have to think of the other terms. Like this, we could call this the A's, the ANs. What are the BNs that you're going to compare it with? You have to come up with that on your own. But I'm going to, let's compare by using, here's some little terminology, only our book calls this the dominant terms. The dominant terms on the top and the bottom. This means like the most significant terms. It usually means something like the highest power on n or something like that. So I'm going to consider on the top just the 3n. I'm going to ignore the 7. And on the bottom, I'm going to ignore the plus 2 and take just the square root n to the 4. All right? These are the dominant terms on the top and on the bottom. Dominant because, between 3n and 7, when n is super big, the 7 really doesn't really matter anymore. It's because if n is like 1,000,000, adding 7 doesn't make much of a difference. And same goes for down here. All right, so this we can actually simplify a little bit, right? That's 3n over n squared, and this is actually 3 over n, right? And so that's what I'm going to use for the b's. So this is going to be my bn, and this, of course, what I start with is going to be my my sequence of ANs. All right. And if you choose the b's properly in this way, when you do the limit, you ought to get a constant which is greater than 0. That's the point of doing this comparison test. We now have to do this lim, and hopefully it exists and is greater than 0. So let's just do it then. So then C is this lim n goes to infinity, an over bn. And you got to plug everything in and simplify as best as you can and take the limit. So up top is 3n plus 7. This is still inside of a lim. 3n plus 7 over square root n to the 4 plus 2, and then dividing that by 3 over n. All right? And you have to work out the weird fractions on fractions, but I believe this is the same as if I just throw the n all the way up to the top, right? and put the 3 on the bottom, like so. I think I did that okay. And then we got to take the limit. How would we do this limit? Anyone want to suggest? This is similar to ones we've done in the past. All right, I wasn't going to say that, but yeah, you could do L'Hopital's rule. Anybody have another idea? Yeah?
Divide everything by n to the 4.
Yeah, these are your two choices, basically. You could try to use L'Hopital's rule or divide out by the biggest power of n. I prefer dividing by the biggest power of n. Although in some kind of weirder examples, you might have to use L'Hopital's rule if you have like sines and cosines in there or something. But anyway, let's, how about distribute the n on top first, and then I'm going to divide out everything by the highest power of n. N to the 4 plus 2. Okay, I distribute the n on top. What is the highest power of n? I say it is n squared. I see an n to the 4 on the bottom, but that's inside of a square root, so I consider that to be like an n squared. I'm going to divide everything through by n squared on the top and on the bottom. 3n squared over n squared plus 7n over n squared. And on the bottom, you put the n squared inside the square root where it becomes an n to the 4. This is a little confusing, but this is how these always go when you're doing this kind of a limit. Yeah?
Would you divide the 3 by n squared too?
No. Because, I mean, this you could interpret as that, right? It is 3n squared divided by n squared. But that's the same as just doing 3 times n squared over n squared.
I just meant in the denominator.
Oh.
You could also divide that by n squared.
No, because it's a coefficient multiple. Yeah. If it were plus 3 plus this, then you would. Yeah. You have to divide every term by n squared. Yep. All right. Anyway, simplify these guys, and then anything which has an n in a denominator becomes 0. So I say just 3 there, and then 7 over n here. On the bottom, 3, 1 plus 2 over n to the 4. Right? And then everything with n's in the denominator becomes 0. So this limit, when I do the limit, is going to be 3 plus 0 over 3 square root 1 plus 0. And the answer is 1, right? I get 3 over 3. Which is just 1. So the limit of all of that is 1. This being a constant greater than 0, so c is greater than 0, so that means the series of an has the same convergence as the series of the bn. All right? This is the conclusion of the limit comparison. What is it, though? Does it converge or not? Well, the series of the bn was, what I say, bn is 3 over n, right? Does that, anybody remember? Is this con or divergent? Divergent. This is divergent. Yeah, this is the harmonic series, or you could think of this as the p series with power 1. P series converges when the power is greater than 1. It diverges if it's less than or equal to 1. So this right here diverges. This is a harmonic, or you could say it's p series, p equals 1. So it diverges, and that means that the other one also diverges. So our original thing, what we started with, I'll just write it one last time. 3n plus 7 over square root n to the 4 plus 2. Diverges. All right? Compared with 3 over n. Any thoughts about that one? This is how it goes. I got one more, and then I have some for you all to try. Once you get the hang of these, I think they're not so tricky. And I hope you agree, I like not having to deal with inequalities. How about this one here? 3 to the n over 2 to the n plus n. That's what I want. We are going to do the same thing. So we need to compare this. That's the big question. What am I going to compare it to? All right. This is my an. What am I going to compare to? as before, I'm going to look at the top and the bottom and consider only what the book calls the dominant terms. So up top, it's just 3 to the n. Like there's nothing, not a big choice to make on top. On the bottom, you have to think to yourself, like when n is really big, what's bigger, 2 to the power n or just n? Any ideas? Yeah, 2 to the n is way bigger than n when n is large, even when n is small. 2 to the n is a big number. So on the bottom, I'm going to say that 2 to the n is the dominating term. It's, generally you take like the biggest power of n, and if it's n to some power. But if it's like an exponential versus a polynomial type, the exponential is always more dominant. All right? So that's what I'm going to compare with. All right, this is my bn. All right, so let's do it. I go lim of an over bn. This is my c. Is lim n goes to infinity. An is what we started with, 3 to the n over 2 to the n plus n. And then I'm dividing by the bn is 3 to the n over 2 to the n. All right, I will write that again, sort of with the right way around. 3 to the n over 2 to the n plus n times the reciprocal of the other thing, 2 to the n over 3 to the n. All right? Simplify as much as we can. We want to do this limit. I would simplify on the bottom, like those 3 to the n's will just straight up cancel, right? So we don't need thems anymore. And then this is lim n goes to infinity of 2 to the n over 2 to the n plus n. All right. And how shall we find this limit? I don't see like powers of n. Ordinarily I would divide out by the biggest power of n. I think in this case you could divide everything by 2 to the n, because I consider that to be like the dominating term. Or you could use L'Hopital's rule here, which I think might be a little bit better. Is that what you were going to say? I know this guy likes L'Hopital's rule.
No, I factored out the 2 to the power of n.
Oh, all right. You did it the other way. Okay. We have different tastes, I suppose. Yeah, I was going to do L'Hopital's rule here, but yeah, you can do either way. Let's just for fun, let's do the L'Hopital's rule. Sorry, I'm letting you down every time.
That's all right.
All right. We're still good. I'm going to do the L'Hopital rule. So anybody happen to remember? So I'm thinking of this as if it was like 2 to the power x. What's the derivative of that? If you're doing the L'Hopital rule, you got to know the derivative on the top and the bottom. Anyone remember? Yeah.
2 to the n times natural log 2.
Yeah, this is a L'Hopital rule step here. 2 to the n times ln2. And on the bottom, I get 2 to the n ln2 plus 1, right? Okay. Is this getting anywhere? I don't know. Actually, this still, if I try to make the n go to infinity, I still have infinity on the top and on the bottom. But I think if we do L'Hopital one more time, this will be all good. So I'm going to do L'Hopital again. It becomes now 2 to the n ln2 times ln2. It's like this ln2 was already there and it stays there. But when I take the derivative of the 2 to the n, I get a new 2 to the n ln2. And then on the bottom, 2 to the n ln2 again, times ln2, right, from the first term. And then the plus 1 goes away because it's a constant which is added to the other part. All right, now everything here straight up cancels and we just get 1. So the c really is greater than 0, which means they have the same convergence properties. Do they both converge or do they both diverge? That's what I want to know. And we look at the b's. This is the sum 3 to the n over 2 to the n. Anybody want to suggest? How do I know? This does fit into the categories that we usually talk about. What kind of a series is that, and does it converge or not?
Geoseries.
A geoseries, yeah.
It diverges.
It diverges. How do you know it diverges?
Because it's greater than 1.
Yeah, what is greater than 1?
3/2.
Yeah, 3/2. So you want to think of this as 3 over 2 to the n. And then that is a geometric series. Whenever you have some number to the power n, that's geometric. So this is, as he said, a geo with r greater than 1, and so it diverges. All right. So the Bn diverges, which means what we started with also diverges. That's the whole point of the comparison test. So that means that the ANs, which is what we started with, 3 to the n over 2 to the n plus n, diverges. Right. This is it. This is how we do it. All right, I got 2 for you to try, and then we'll go on to something different. In each case, your job is just say, does it converge or diverge? There's one, and here's one. See what you think.
That's a good point.
here. Still good here? Yeah, that's when you talk about the geometric series, that's some but here, yeah, this is all that's up. That means that this thing has the same convergence as this. That one converges. Yeah, it does. Yeah, this is a P series. P series means one converges to P, and if P is greater than one, it converges. Still good here? Yeah, you don't have to do short. It's just a constant. All right, you want to chat about these? So for the first one, pretty much everybody said the bn's should be n to the 4 over n to the 7. I find it easier to just simplify that from the get-go, although some people left it as 4s and 7s the whole time. It's not wrong, it's just you'll have to simplify it eventually. Anyway, then I do an divided by bn, which I write as, I find it easiest to just write this as an times the reciprocal of bn. So that's why it looks like this. An times the reciprocal of bn. And now we have to find this limit. I would distribute the n cubed up top. Distribute the n cubed up top. It'll say 5n to the 4 plus n to the 7 over n to the 7 plus n to the 5. Right? And then we, I saw a fair amount of bogus canceling as I was going around. Please don't do like this, right? This sort of makes baby Jesus cry, as they say. You can't do that. If they are added together, you can't cancel like that. So don't do it. Instead, just do this limit by dividing through the biggest power of n. Or you could use L'Hopital's rule, or you can, some people learn to just sort of remember, if you have a ratio of polynomials, and the degrees on top and the bottom are the same, then the limit is equal to the coefficients, the leading coefficient on the top and the bottom. This would be 1 here divided by 1 here. The ratio of the coefficients, that's what I'm talking about. Anyway, this I would, if we're dividing through by n's, n to the 7, it would say 5 over n cubed plus 1 over 1 plus n to the 5 over n to the, 1 over n to the 2. I'm trying to simplify. Those parts become zeros, and I just get 1 as the answer. All right, so this one is, the limit does exist and is greater than 0, so we can do the comparison test, and that means that The original series has the same convergence as this one, and this one converges because it's a p series where p is greater than 1. So this converges because it's a p series, p greater than 1. And so that means the original one converges. The OG series converges. All right. As I was going around, this is what everybody seemed to say. Any thoughts about that one? All right, the other one is maybe slightly more interesting. I don't know. So this one, I choose the dominant terms on the top and the bottom, and that's going to be 2 to the n and 5 to the n, like that. And then we do the comparison. So the limit an over bn will be, I'll write this as an times the reciprocal of bn. So it's n plus 2 to the n over 5 to the n times the reciprocal of bn. That would be 5 to the n over 2 to the n, right? The 5 to the n's cancel entirely, and then the other stuff remains. N plus 2 to the n over 2 to the n, right? And then from here you can do this limit by doing L'Hopital's rule, or you can just divide everything out by 2 to the n. Maybe I'll write it that way just for the sake of variety. Divide everything out by 2 to the n. It'll say n over 2 to the n plus 1 over 1, right? And that says n over 2 to the n. It's a little weird looking. But anyway, this is lim of n over 2 to the n plus 1, right? And what is the n over 2 to the n? I suppose you're going to have to use L'Hopital's rule at some point, but this is 0 because I could do, if I'm doing n going to infinity, this looks like infinity over infinity, but if I do L'Hopital's rule once, it'll say 1 over infinity, basically, and that will be 0. So if you do L'Hopital once, you'll get 1 over 2 to the n, natural log 2. And now that first one is 0 when I take the limit. All right. So this is the comparison for this one. So my limit is greater than 0, which means the bn and the original thing have the same convergence. And what is the convergence of the bn? This is the sum 2 to the n over 5 to the n, which I write as 2/5 to the n, and that converges. This is a geometric series with r less than 1, right? In absolute value. Okay, and so that means the original series converges. The end. All right. Any thoughts or questions about these? To me, these are fairly straightforward. If you know what you're doing, you just kind of work it out. You don't have to think all that much about it, which is better than the other comparison tests, which, in my opinion, you kind of do have to think a little bit harder to do. All right, great. Let's move it on to the next thing then. This is the end of the comparison test stuff. Let's just get on with the next test. Then there is another test. So the ones that we've seen so far are the integral test, and I'm just going to talk about the requirements. The integral test requires that the function is decreasing always. And then the one we just talked about, the comparison test, requires that the terms are always positive. All right. Let me just say, neither of these tests, I'm talking about the integral test, nor the comparison. Look at me, I use the word nor properly. I never say the word nor, but it's a special treat for today. Neither the integral test nor the comparison test can handle an alternating series. Alternating, that means, the terms go plus positive and then negative and then positive and then negative, right? Because an alternating series, the terms, like I just said, they go positive and then negative and then positive and then negative, right? Alternating in sign. And there are lots of important examples of this. Alternating in sign, right? But if they do really alternate positive then negative, then actually that automatically means we can't use either of the tests we've already talked about, because the integral test requires the sequence is decreasing, and an alternating sequence like this is never decreasing because it's constantly bouncing up and then down and then up and then down. So such a thing can never be a decreasing sequence, and it also can never be a sequence where all the terms are positive, so you can never use the comparison test either. All right. This is a series, I'm drawing a sequence which is alternating in sign. And none of our tests can apply to that. That's why we have a special test to use in this case, and this is called the alternating series test. All right, so this is one in which this one really only applies to a series where the signs are alternating. All right. And this is the setting in which you want to use the alternating series test. One bit of bad news about the alternating series test is it can only show that a series converges. Actually, you cannot use this to show that something diverges. You can use to show that it converges, and if the test doesn't work, you still don't know if it converges or diverges. So it applies to series where the signs are alternating, and I will say can sometimes show it converges. The alternating series test actually can never show that something diverges. Even if it does diverge, the test will not show that. All right, can sometimes show that it converges. For example, the classic example. Well, there are. How about this? This is the classic example of an alternating series, and this is referred to as, for obvious reasons, this is called the alternating harmonic series. If I didn't have the minus 1 to the n, like just 1 over n, that's the harmonic series. If you put minus 1 to the n up top, that is called the alternating harmonic series. If you were to write out the terms, it says minus 1 plus a half minus a third plus a fourth minus a fifth, etc. Right? That's the alternating harmonic series. Now, just 1 over n diverges. We've seen that many times. So that means if you put plus signs on everything here, then it diverges. It goes to infinity. But actually, if you flip-flop the signs every time, then it's not clear what's going to happen, because there will be some kind of cancellation here, right? If they were all positive, it would be infinite. But since about half of them are negative, you might feel like, well, maybe it kind of evens out, and you don't get infinity. You get, I don't know, 0, or maybe you get just like some other number. This is what we want to think about. This is called the alternating harmonic series. And of course, many other alternating series are of interest. So I will say generally, we'll come back to that specific example and do it. That's actually a very easy one if you know the alternating series test. Generally, it looks like, something minus something else plus something minus something plus something minus something plus, etc. Right? This is what an alternating series looks like. It alternates the signs in between each of the terms. All right? Or you could say, so that's what it would look like if you wrote the terms out. You could also consider what the graph of such a thing would look like. It means it starts maybe up here and then they go back and forth, right? Alternating, something like that. All right. Will it converge or not? So, first of all, just because it alternates doesn't mean that it automatically converges. Like we've already seen, for example, we talked already about just this example. This is alternating. It's just minus 1 plus 1 minus 1 plus 1, and that diverges. That was one of the first examples we ever talked about. This diverges. Sometimes they converge, though. That one doesn't. here's what it takes to converge. So it turns out it will converge if the terms, the individual terms, decrease to 0. And what that would look like, so by decrease I mean in their absolute values. Because of course from one term to the next it can't always decrease because it has to be jumping up and down as you go. It's always jumping up and down. But I mean if the terms in their absolute values decrease to 0, that means something like the first one is way up there. I have to jump back and forth, but I'm making it so that as I go, they get closer and closer to 0. All right? That is certainly possible, and it turns out in this situation, the series will converge. So I'm going to write that out. I mean, this is the whole basic idea of it, but I'm going to write that formally speaking, and then we'll try some examples. So I'm going to write this as a theorem, and this is called the alternating series test. And it says very specifically, so if we have a series like this, I meant to say, in this series, this is how our book writes it. B1 minus B2 plus B3 minus B4 plus etc. All right? Every alternating series can be written in this way. Now here I'm assuming the first one is positive and the second one is negative. The exact same thing is true if you have the signs flip-flopped the other way, as long as they always alternate back and forth. All right. Anyway, in this series, there sort of two things have to be true. If bn plus 1 less than or equal to bn, that is to say the bn is decreasing, and the lim of the bn's equals 0, then the series converges. All right, this is the alternating series test. So if you want to show the series converges, there are two things you need to verify. This and this, all right? The decreasing part and the limit part. These are two separate things, and you just have to work them out separately in order to show that the series converges. The individual terms, if you ignore their signs, have to be decreasing, and the limit of those terms have to go to 0. That's what I said in words a moment ago. It will converge if the terms decrease to 0. That's what I meant when I said, or that's what I was talking about when I was saying it less formally. First of all, they decrease, and second of all, they actually go to 0. All right. Maybe you're wondering, if they're decreasing, doesn't that automatically mean they go to 0? It's not true. Something can decrease and say approach 1 from above, right, without going to 0. It can go approach something else. This is saying that the terms actually have to approach 0 while decreasing. All right, and in that case, the series converges. All right, can I give you a little idea about why you should believe this? I'm talking about, like I said, something like a sequence. I'm going to try to draw a picture of a sequence which actually has these properties that I'm talking about. The terms themselves are getting closer to 0 as you go, even though they're bumping up and down. I would like to know, how do you know that this actually converges when you add it all up? Like this height would be B1, this here is B2, that's B3, etc., right? What about if we add them? I'm going to add them kind of horizontally instead. Let's say here's 0. I'm just sort of thinking about what happens on a number line if I add them up. When we add, we begin with B1, which according to my picture, like B1 is positive. So if I'm starting at 0, I add B1, it's going to like jump over this way a bit. So here I add the first term, that's B1, all right? Now, this is, I'm thinking of taking like a running total as I add the terms one after another. The first term makes me jump out to the right. That's B1. The second term is B2, but it's negative, and so when I add that on, I go back to the left in my running total. And I ask you, when I go back to the left, am I going to go past 0? The answer is no, because the B's are required to be decreasing. That means B2 is automatically less than B1. So it means when I jump back to the left, when I add in B2, I do not overshoot the 0. I actually end up in here somewhere, right? So the next term, B2, kind of bounces me back a little bit to the left. What about B3? B3 bumps me back to the right a little bit. But again, because the B's are decreasing, the B3 is smaller than the B2, when I pop back to the right, I'm not going to go out here. I'm going to end up, say, somewhere like over there, right? This is like B3. Each time your running total is going to bounce back and forth, but only a little bit, right? So the only way this is possible is if eventually, as I'm adding these numbers, they actually converge to a particular point, right? Because each time you add a new number in, it has to bounce back either to the left or to the right. But because the terms are decreasing, it never bounces outside of this sort of like funnel here. And so eventually the total sum will converge. All right? It's because, first of all, each new addition either sends you to the left or to the right again, and each new addition is smaller than the previous one, and so they eventually have to stabilize somewhere. All right. This is the idea behind the alternating series test. Now, to actually do examples, you don't really have to think through this, but that's the idea of why it works. Maybe we'll just try some examples. Let's try this. The simple example is the alternating harmonic series. All right, to the n-1 here. This is the alternating harmonic series. Now, we have to first off just decide what the B's are. This is my original series. I'm going to kind of pull off that thing. I'll write it that way just to isolate. This is the alternating part. This is the alternation. You know, the signs. I wrote alteration. I meant to write alternation. But anyway, that is what we really care about. That's what the Bn is, right? The Bn is the sequence of numbers without the signs, just the numbers. And they are automatically going to be all positives, just the Bn's, all right? So in our case, Bn is 1 over n. You always have to take what you're given and just kind of like strip out the signs, ignore the alternations. That's what the Bn is, 1 over n. And then we have to demonstrate, according to the theorem here, both of these things must be true, and then you can conclude that it converges. So we need to show, we'll show, first of all, that Bn is decreasing, and second of all, that the lim of Bn equals 0. Those were the two things which I underlined in red up there. This is always what you have to do to use the alternating series test. And these two parts, I would say probably the second one is usually easier. You know, to show something is decreasing is sometimes a pain, like this is what we did on the quiz last time. Yeah?
You need to show the conditions for the test to like prove that they're accurate.
Usually I would say no. Yeah. Although technically I suppose you should, but yeah. In this one, I would expect you to show these just because otherwise you're not going to do anything. Like this is sort of the whole problem in one like this. Yeah, that's a good question. From a theoretical point of view, you really should be proving the assumptions are true in every example. But, yeah. Okay. Anyway, let's try this. So let's do the decreasing first. All right. I need to show. Maybe I'll write WTS. That means I want to show. As I was reading your homeworks and the quizzes too about the decreasing, I was a little dismayed that some people, some words haters didn't write any words anywhere. You should write at least some words in when you are doing one of these little proofs about increasing or decreasing. Anyway, in this case, I want to show bn plus 1 is less than or equal to bn. That's what it means to be decreasing. It should be strictly less. That is a technicality that doesn't really matter, but this is how our book defines decreasing. All right. So what does that mean? This is the same as bn plus 1 would be 1 over n plus 1. Here's the bn, right? And so bn plus 1 just means you do this, but use n plus 1 instead of n. And then the right-hand side is 1 over n. All right? And is that really true? We're going to just sort of simplify. This is a very easy example of one of these. I would multiply the denominators across. This is the same as n less than n plus 1. This is true, right? N is always less than n plus 1. If that's not obvious enough for you, you could subtract the n's. It'll say 0 less than 1. And that is true, all right? So this is the end of showing that it decreases. We've already done much more complicated examples than that, but this is an easy one for decreasing. All right, you should write some words though. Like, you don't have to write a lot of words. Some words like this. If all you write is something like that, if you just write that with no words anywhere, it seems to me like you have just proved 0 is less than 1, which is not really the point. The point is, what we need to show is this, and we showed that that's the same as something which is obviously true. That's a logically a different kind of argument, and you need to have some words in there to signal that. All right. Anyway, we are halfway done. That is to show that it decreases. The other is to show the lim. Okay, so there's always like the decreasing part and the limit part. So this time we need to find the lim, n goes to infinity, 1 over n. But this is very easy. This is 0. And that's what we wanted, right? In the limit part, you have to show that the limit equals 0, which it obviously does in this case. All right? So it's decreasing and the limit is 0. That means that it converges. The sum minus 1 to the n over n converges. Because it is those b's are decreasing, and also the limit of the b's is 0. All right. This is a strange fact. Remember what I'm talking about here? This is minus 1 plus a half, minus a third, plus a fourth, minus a fifth, right? This actually does add up to a specific number. Anybody happen to know what this adds up to? It's a fun fact. This is, it adds up to, starting with a minus sign, it adds up to negative ln of 2. How you like that? It's true. But this is very weird. In order to actually calculate this is a totally different thing. So maybe I'll put this in parentheses. Right, the alternating series test doesn't tell you that. It only tells you if it converges or not. We are actually going to do some stuff which will allow you to calculate this later on, but not today. All right, not this day. Let's try. I got another, and then I have some for you all to try. Yes. How about, that was an alternating harmonic. How about something like an alternating geometric? How about something like this? 1 minus a half plus a fourth minus a eighth. All right. This one is a geometric and alternating. Now, actually, you can do this one just by thinking of it as a geometric, but I want to try to do the alternating series test. So let's show it converges using the alternating series test. All right. In this case, it's not really necessary. If I wasn't telling you to do it in this way, it's much easier actually to just think of this as this is geometric with r equals minus a half. And so you can do the a over 1 minus r thing for this. It does converge by that. But I'm trying to use the alternating series test instead to demonstrate that. All right, so in this case, what is my b to the n? You have to think about the b's, right? Because all the things you're arguing here are actually about the b's, not about the original thing. The b's are the original series, but with pluses everywhere. So the bn sequence is 1, a half, a fourth, a eighth, etc. Can anyone give me like a real formula for that? Rather than just writing the terms. A general formula. What I see, you want to like think about what's the pattern. I see powers of 2. Yeah. 1 over 2 to the n. Yeah. Although I'm not sure about n equals 1. If I use n equals 1, I get a half here. It's, yeah, some. Yeah, this is a cute little variation. Yeah, you need 1 over 2 to the n minus 1. That n minus 1 doesn't make a big difference, but it is technically what we're talking about here is 1 over 2 to the n minus 1. All right, anyway, this is our b's. So let's just do the two things. You got to show it's decreasing and then also that its limit is 0. So let's do the decreasing first. I want to show that bn plus 1 is less than bn. That is to say 1 over 2 to the n plus 1 minus 1 less than 1 over 2 to the n minus 1, right? And let's simplify. I mean, on the left you have a plus 1 and a minus 1, which can just cancel, right? So this is the same as 1 over 2 to the n less than 1 over 2 to the n minus 1. And then we can do our little multiply the denominators across like we always do. It'll say 2 to the n minus 1 on the left less than 2 to the n. Can anyone suggest how we can simplify something further? Maybe that's obviously true, I don't know. We can write it a little bit better to make it even more obviously true. Yeah? I wasn't going to do that. He said take the ln on both sides, which is not a bad idea when you have n inside the exponent. Like if I wanted to solve for n, I would do that. I think there's something simpler you can do in this case. I would also feel weird about when you take the ln. Can you take the ln on both sides of an inequality? If so, should you switch the sign around? These are deep questions that you should ponder about. The answer is, in general, you cannot. If you have an inequality, you can't just do whatever you want on both sides and expect things to work properly. Although the ln turns out it does work with. You got another idea?
Can you just say n minus 1 is less than n? Is the basis of the same?
N minus 1 is less than n. That's true. Although I have a better, I don't know, I was thinking of some other way to simplify this. Yeah?
2 to the power of n plus 2 to the power of negative 1.
You're going to rewrite 2 to the n minus 1 in this way?
Yeah.
Is that what you're saying? Yeah, 2 to the, yeah, this is along the lines, although I think you said plus, but I would say it this way.
And then you just subtract 2 to the n from both sides.
You divide 2 to the n on both sides. Yeah. This has to be a multiplication here because that's how exponents work. Yeah, and then I would divide out 2 to the n on both sides. This is what you were saying, right? It's at least the same as what you were saying. Divide 2 to the n on both sides. This now says 2 to the minus 1 over here. Come on now. 2 to the minus 1 less than 1, right? I divided. And is that true? 2 to the minus 1 is a half, right? Yes, this is really true. Yeah, something like that. Actually, I was gonna just like from right here. This is pretty much the same as what he was suggesting. But if we divide by 2 to the n on both sides, on the left it says 2 to the n minus 1 over 2 to the n. Oh, thought it was your phone again. It's not. That'd be a sick ringtone though. All right, like this. If we divide on both sides by 2 to the n. 2 to the n over 2 to the n will cancel. I get 1. Over here, you should be subtracting the exponents. This just says 2 to the negative 1 less than 1, which ends up at the same place. So these are two different ways, if you like, you could have simplified this thing. All right, anyway, it is decreasing because 1/2 really is less than 1. That's the end of the story here. All right. Okay, that was half of it, right? You have to show it's decreasing. And now I also have to do the part with the limb. So this is just limb n goes to infinity. And this is going to be easy, right? That's the sequence. What is that limit? It really is 0, because this is going to be basically 1 over infinity. When you let the n go to infinity here, this limit really is 0. And so that means these two things together means that the alternating series minus 1 to the n times 1 over 2 to the n minus 1 converges. Right? Sorry, I think we started with a positive, so this also needs to be a minus 1. It doesn't matter. They both converge, but I just changed the exponent here. All right, this is the alternating series test. I got one for you to try. So you have to do the decreasing thing, and then you also have to take the limb. So you try. Your job is to show that this converges. See how you like it. You started writing that. That's the same distance. Let's see. Write something like this is the same as this. Okay. Those are the words I want. How's it going? Doing good here?
Yeah, I can't think of
Let's say right here. This is obviously true to me. Because this stuff is positive.
Yeah.
So let's say here. Well, I got 6's here. 3%. Doing good here? Okay. All right, let's talk about these. Folks seem to be doing okay. Although I still feel like there's some word haters in the room. You got to write some words when you are writing proofs that are logically backwards. Oh, it's snowing. Just so everybody look. The fluttering snow. Yeah. Okay, let's do, first of all, what are the B's? The BN is just the sequence in there, just without the signs, right? We just consider everything as if it were positive. That's the B's. And then, first step is the decreasing step, all right? I want to show that BN plus 1 is less than BN. That is to say, and here you have to, do some work. But I'm going to plug in n plus 1 on the left side, like so, less than 2n over 3n squared minus 1, like that, right? I rewrote that in this way. Now, can I just say something about the words? I don't really care that much about you guys like writing some kind of a essay or whatever, but the words are important because what you are arguing here is actually logically backwards, all right? I'm starting by writing what I want to be true, and then I again write what I want to be true. This is what I want to be true. An ordinary sequence of steps, you start with something you already know is true, and then you say this means this, and this means this, and this means this, and I obtain something else, which I didn't know was true before, but I just proved that it was true. This, when you write it, is backwards because I'm starting by writing what I want to show, and I eventually end up with something which I already know is true. The fact that I'm writing a backwards logical argument is why you should put some words in here to explain that what you're writing is actually logically in reverse. So anyway, this is what I want to show. This is the same. You can just say IE every time or something like that. I will distribute the 2 up top. Do on the bottom, do the FOIL, and then distribute the 3. It should look like 3n squared plus 6n plus 3 and then plus 1. Less than, the same business over here. Maybe I will just add on the denominator again. 3n squared plus 6n plus 4. 2n over 3n squared minus 1. How am I doing so far?
Why does
Not
it
good?
have plus 1?
Oh, one of them has a plus 1 and the other is a minus 1. It should have been a minus 1 both times. Yeah, thank you. So that actually is right here. Right here, minus 1. Minus 1. Right? Okay, so this should say plus 2. Sorry about that. Everybody feeling all right about this? All right. It's easy to mess up, as I said. Now I multiply across. It will say 2n plus 2 times 3n squared minus 1 less than 2n times that other stuff plus 6n plus 2. Remember this, logically speaking, this is still what I need to prove. This is not something that you already know is true. This is what I need to prove is true. That's why I put all of these things here. All right, and now distribute on the left. It says 6n squared plus 6n cubed on the front. The inside term is 6n squared. The outside term is minus 2n, and on the very end, minus 2. And then on the right side, less than, distribute there. 6n squared plus 12n, cubed. I did it again. 6n cubed plus 12n squared plus 4n. And then simplify. I will maybe put all the n's on the right side and just leave the constant on the left side. So 6n cubed straight up cancels. I have 6n squared, which I will move to the other side. It will combine with these 12n squareds and give me just 6n squareds. Sorry. I believe it's like this. That's what I get when I move them all over to the other side. I saw several variations on this. I think it's easy to mess up the details in here, but anyway, I say this is obviously true because the thing on the left is negative and the thing on the right is always positive when I'm using positive whole number values for n. So this is true. And so that means that bn plus 1 really is less than bn. All right? Let me just say again, if you don't write any of these words, and you just sort of like, some people, the most egregious thing is when somebody writes all of this stuff with no words, and then they're like, yes, circle that thing at the end, as if that's what you're proving. This is not, in fact, what you're proving. What you're proving is what was at the very beginning. This is an obvious thing which justifies why all the things above are also true. Yeah?
What does I.E stand for?
I don't know. Is it some Latin thing? I.e., it means something like that's the same as this. Like after class I'm gonna make dinner for a lovely lady, i.e. my wife or something. That's how you use i.e., something like that. In other words, something like that, right? E.g. means for example, which is sometimes also appropriate. Okay, anyway, the decreasing. This, I hope you wrote something like this, and I hope you wrote at least some words to signal to the reader, i.e. me, that you understand that you're writing a backwards logical argument. There's nothing wrong with writing the logic in a weird order. It's just you have to indicate that to the reader. Okay, and then let's just finish this. Before this step is a little more straightforward. Typically, we have to take the lim of the bn's, and that is 2n over 3n squared minus 1. How do we do this lim? This is an easy limit. It is one of these ratios of powers of n, so I would divide out the biggest power on the top and the bottom, so that I would write 2n over n squared, and then 3n squared over n squared minus 1 over n squared. This ends up being 2 over n, still inside the lim, 3 minus 1 over n squared. And then when I do this limit, I get 0 over 3 minus 0, which is 0. And so the limit of the bn's is also 0. All right? So in conclusion, I said decreasing and limit equals 0 means it converges. All right, I think that'll do it for today. I got one more example of this, and then we'll talk about something else. Yeah.